right, pre-cal, this is the last video of this school year. We are finally going to be done. I know some of you are very excited. I'm a little sad because I really like this class, but summer must come. Big shout out to Hannah Bryant, who unknowingly doesn't know that I have borrowed your locker shelf so that I can make some of these videos, because my locker shelf somehow went missing from my garage, and I think perhaps my husband might have thrown it away on accident when he was cleaning out the garage recently. So I borrowed your locker shelf. I'll put it back in there as soon as I'm done making these videos. I meant to tell you and I forgot, and I just realized that now as I looked at this locker shelf. So thank you, Hannah, for letting me do that. Okay, so we're going to talk about geometric sequences. Now remember, in the last video we talked about arithmetic sequences. We said that an arithmetic sequence is one where you have a common difference between each term of the sequence. If it's a positive value, that meant that your sequence was increasing. If your value for D was a negative value, it meant that your sequence was decreasing. So for geometric sequence, this time instead of a common difference, because for geometric sequences we are multiplying by the same value every time. Instead of adding the same number every time, we're multiplying by the same number every time, and that number we call it the common ratio. So you're going to see the letter R. No, that doesn't stand for radius. It stands for the common ratio. So we're multiplying by the same number every single time. It might be positive, it might be negative, could be either. So let's take a look at letter A. We want to determine whether the sequence is geometric or not. So if we can find what R is, then we'll be able to say yes, it's geometric. And if we cannot find a value for R, then we're going to have to say no. So as I take a look at the numbers, I'm going from 1 to 2, and then from 2 to 6, and 6 to 24, and 24 to 120. Now I do see a pattern. To get from 1 to 2, I could multiply by 2, and to get from 2 to 6, I could multiply by 3, and 6 to 24 would be multiplying by 4, and 24 to get to 120 would be multiplying by 5. However, I'm not multiplying by the same number every single time, so for this one I'm going to say that it is not geometric. So even though there is a pattern, and even though there is multiplication going on, because we're not multiplying by the same number, it can't be a geometric sequence. Let's look at letter B. Now the numbers are getting smaller. In the last one with the arithmetic sequences, when our numbers got smaller, it meant that our value for D was negative. Not the same here. If you look at these numbers, what you might be able to tell is, hey, I could divide by 3 to continue getting to the next number. But according to our definition for geometric sequences, we want to talk multiplication, not division. So what could you multiply by? Well, what's the reciprocal of 3? It is 1/3. So if we multiply by 1/3 continuously, that's where this sequence would come from. And so that means that this is geometric. All right, the next one, we're going from 4 to -8 to 16 to -32. What could happen? Well, to get from 4 to -8, we could multiply by -2. Would multiplying by -2 get us a positive 16? Yes. Would multiplying by -2 get us the next number of -32? Also yes. So our value for R is -2, and that means that this is a geometric sequence. Now, if this seems familiar, for those of you that had me for Algebra 2 last year, it should be, because we learned the same lesson last year. All right, last one. 3 to 9 to -27 to -81 to positive 243. Well, to get from 3 to 9, I can multiply by 3. To get from 9 to -27, I have to multiply by -3. Right? Yeah. To get from -27 to -81, I would multiply by 3. To get to the next number, I would have to multiply by -3. There's definitely a pattern, but it alternates numbers, right? It does a positive 3 and then a -3, and then it keeps doing that. So this is not going to be geometric. So you have to be multiplying the exact same number every single time for this to be labeled a geometric sequence. All right, so we've got some more formulas. Yay, formulas. This formula will help us find the nth term of a geometric sequence. So we need to know the first term of the geometric sequence. We need to know the common ratio, and then n stands for the number of the term that we want. So for example 2 and example 3, we're just writing a rule, which means we're writing an equation. We're not actually going to plug a number in for n because they haven't asked us to find a specific term. We just want to find an equation for the nth term. So first thing I know is that the first term is -8. I now need to figure out what the common ratio would be. What could I multiply to get to the next number? Now sometimes you get a sequence and right away you might not be able to figure out what that common ratio would be. And that's totally okay. But what you can do is go off to the side of your paper because they're already telling you, hey, this is going to be a geometric sequence. We already know that's the kind that it's going to be. So we're going to figure out what the common ratio is. So if I have the first term of -8 and I multiply it by r, which I don't know yet what it is, but I know that the next term is -12. I could use this simple equation and solve for r. So I'm going to divide both sides by -8. Now it doesn't go into -12 evenly, but negative divided by negative turns into a positive, and 12/8 reduces to 3/2. So we do now know that the common ratio is to multiply by 3/2 every single time. So we're going to have a sub n equals a sub 1, which is -8, times r, which is 3/2. And I like to put mine in parentheses, and then we're going to raise it to the n-1 power. And that's it. That's just writing the equation or the rule to find the nth term. So we're going to do the same thing for number 3. I know what the first term is. It's 5. Now let's talk about what r is. Maybe I don't recognize it right away. No big deal. 5, the first term, times r will give us the second term, which is 2. So I've got an easy equation. I'm going to divide by 5 on each side and find out that r is 2/5. So I'm going to have a sub n equals the first term, which is 5, times the common ratio, which is 2/5 raised to the n-1 power. And that's all we have to do to find the rule. Pretty easy, right? Okay, so example 4 says find the 8th term of the geometric sequence 5, 15, 45. Okay, so real quick, let me just write the formula down. Right there. Okay, so according to this, I need to know the first term, and it is 5. I need to know the common ratio. You guys can probably look at it and tell me the common ratio is 3, right? We're multiplying by 3. And in this particular problem, because we want to find the 8th term, that means that n is 8. So I want to find a sub 8. I'm going to plug in the first term, which is 5. I'm going to multiply that times a common ratio of 3 raised to the 8-1 exponent. So 8th term is 5 times 3 to the 7th power. Remember your order of operations. You got to do the exponent first. So here we go. Let's just plug it in. 5 times 3 to the 7th power. And we're getting 10,935. And yes, you'll be allowed to use a calculator. I would not expect you to be able to do that one by hand. You could do it by hand, but that's tedious and silly, and we're not going to do that. Okay, so next example says the third term of a geometric sequence is 63/4. The sixth term is 1,701/32, and we want to find the fifth term. Okay, so if you remember in the last video when we did the arithmetic sequence, we said, okay, we need to know the first term, we need to know n, we need to know the common difference. But sometimes we found out that we were not given the first term, and so we changed our formula a little bit, didn't we? let's see what they gave us. They're telling us that the third term is 64 over 3. We've also been told that the sixth term is 1701 over 32. Now let's write down the formula real quick. So we know that it's a sub n equals a sub 1 times the common ratio to the n minus 1. Much like what we did with the arithmetic sequence, notice that this is a 1 and this is a 1, but I don't know the first term. So what if I change the 1's, just like I did with the other ones, to a k? So I have to know some other term, and then I would raise that to the r to the n minus k power. Now, just like when we did the arithmetic sequence, obviously n needs to be a larger number than k does. Think k comes first in the alphabet, so k needs to be the smaller number. So for this particular problem, the 3 is going to be the k because it's smaller, and the 6 is going to be the n, and we're going to plug this in because we have to solve for r. We have no idea what r is. So here we go. So that's a sub 6 equals a sub 3 times r to the 6 minus 3 power. Now let's plug in what we know. We know that a sub 6 is 1701 over 32. We know that a sub 3 is 64 over 3. And 6 minus 3 turns that exponent into a 3. All right, so before I can solve for r, I first need to get r cubed by itself. So I need to get rid of 64 over 3. How do I do that? I'm going to multiply both sides by the reciprocal, which is 3 over 64. Now, I would be willing to bet that we can do a little bit of cross-canceling. So let's see. Oh, you know what? Womp, womp, womp. Okay, go back, guys, because on my smartboard notes, this is a 4, and then somehow on the paper, it's a 3. So we're going to change all of that to no. Oh my gosh. Wingard, you messed up. Okay. Ha. I know what happened. Okay, that's supposed to be a 63 over 4. Probably should have figured that one out before I started going through this whole problem. Lo siento. That's Spanish, y'all, for those of you in Spanish. Hopefully you know that means I said, I'm sorry. Oh my goodness. All right, fixing it up. No big deal. We're changing that to 63 over 4. Is everybody good? Has everybody had time to erase like I did? Okay, so back to where we were. We want to get r cubed by itself. We need to get rid of 63 over 4. How shall we do that? We will multiply it by the reciprocal, which is 4 over 63. I knew something wasn't right when things weren't going to cross cancel out, because they should. Okay, here we go. So 4 and 32, can y'all see it? I am off my game tonight. All right, 4 and 32 can cross cancel, right? They're both divisible by 4. So the 4 turns into a 1, the 32 turns into an 8. You might not know this next one, but 63 and 1701 are both divisible by 63. So 63 turns into a 1, and 1701 turns into a 27. So what we have is 27 over 8 equals r cubed. All right, how's everybody doing? Hopefully we're doing good. How do we get just plain old r? Well, you got to cube root both sides. Great news, y'all. Those are perfect cubes. 27, the cube root of it is 3. 8, the cube root of it is 2. So r is 3 over 2. How's everybody doing? Hopefully we're doing pretty good. Okay, now let's go back to this formula right here. I'm putting the k in here, and the reason why is I still don't know the first term, so I'm not going to go back to the other formula. What are we being asked for? We're being asked to find the fifth term. So I'm going to make n now 5. Now normally I would say you could use either of these that you want, but which one would it not make sense to use? it wouldn't make sense to use this one, because remember, we need this number over here to be bigger than whatever k is, and 5 is not bigger than 6. So we're going to continue to let this 3 be the k. So a sub 3 times r to the 5 minus third power. Okay, so a sub 5, that's what we're trying to find. We know that the third term is 63 over 4. We now know that the common ratio is 3 over 2, and we're raising that to the second power because 5 minus 3 is 2. So we got to do order of operations, which means we have to take care of the exponent first. So 3 halves squared is 9 fourths. And I don't think anything can cross cancel. So we're going to multiply straight across. So 63 times 9 is 567, and 4 times 4 is 16, and that is the final answer because we are looking for the fifth term. Okay, so recap real fast. Just like with the arithmetic sequence, sometimes you're not given the common ratio. Like in the last video, we weren't given the common difference. So we had to change our formula up, replace the ones with k's, used what we had to find the common ratio, and then we were able to use that common ratio to then find the term that we were looking for. So at that point, it's a bunch of algebra, right? All right, partial sums. So again, we've been learning about partial sums. That means you're adding up however many terms you're being asked to add up. So if we were trying to find s sub 4, we would add the first 4 terms in whatever that sequence is. Well, with the arithmetic sequences, remember we learned some formulas to find partial sums if it was an arithmetic sequence. Well, we also have a formula for a partial sum of a geometric sequence. So this is what it would look like. You need to know your first term, you need to know your common ratio, and obviously you need to know what n is. How many of the terms are we trying to add together? So let's take a look at example 6. Find the sum of the first 5 terms of the geometric sequence that we have right there. Well, we already know it's a geometric sequence, so that tells me that we need to find the r. How do I get from 1 to 0.7? So if you didn't know this one off the top of your head, you would say, okay, hey, the first term times r equals the second term. So for us, that means r is going to be 0.7. So we know the r. We also know the first term, right? It's 1. And we also know n, because they're telling us the first 5 terms. So we're going to find s sub 5. So I'm going to plug in the formula. So I've got a 1 in place of a sub 1. In the numerator, we're going to do 1 minus 0.7 to the 5th power. And then in the denominator, 1 minus 0.7. Again, I wouldn't expect you to do this without a calculator. I'm going to go back to my calculator. I'm actually going to put mine in math print because this will make it so much easier, at least the way that it looks for me. Okay, so let me get rid of that. So we have the a sub 1, and then parentheses, got a fraction. I'm going to do 1 minus 0.7 raised to the 5th power. Then I'm going to go to the denominator, 1 minus 0.7, and then I'm going to close the parentheses. So I'm just plugging in what I have written on my paper, and we're going to get 2.7731. So if we added the first 5 terms together, that is the sum that we would get. Pretty easy. All right, example 7. Here's what I want you to notice. See this thing right here? It's already written in the form of what a geometric sequence would look like. That tells me this is the first term. That's the a sub 1. That tells me that that in parentheses, the 2/3, that is the common ratio. Wait, actually, don't necessarily say that's the first term. Here's why. Because according to that, this formula, we have n minus 1, and we don't have an n minus 1. But what we do know is we have the common ratio. All right, but we know that it's a geometric sequence. So it says find the sum. Now this is telling us, remember we learned about this earlier in a video, that this is sigma notation. This tells you to go from the first term to the fifth term. So what we're looking for is S sub 5, just like we were in this last problem. We need to know what the first term is. So I'm going to actually just use the formula. 7 times 2/3 to the first power. I want to know the first term. I'm plugging in a 1. Does that make sense? Which is just 7 times 2/3, right? Because 2/3 to the first power stays the same, and that is going to be 14/3. So there's the first term. Now parentheses. All right. Now we're going to do 1 minus, remember we already identified R as 2/3, and we're going to raise that to the fifth power. And then in the denominator, 1 minus 2/3. How's everybody doing? Pretty good? Ooh, I moved the camera on accident. Whoops. Okay, let's go back to math print and plug it in just like we see it. So the first term is 14/3, then parentheses, then I got a fraction. In the numerator, I'm going to do 1 minus 2/3, and then I'm going to raise that 2/3 to the fifth power. Then in the denominator, I've got 1 minus 2/3. And then we're going to close it up. All right, everybody see it? How I've plugged it in? I'm going to hit enter. Look at that. Man, I love math print on a calculator. So we have 2,954 over 243. 2,954 over 243. Love it. Okay. So this next one is a different formula, and it is for the sum of an infinite geometric series. Infinite meaning it goes on forever and ever and ever. So basically what happens with these is we're finding what it's going to get close to. If you were to continue adding these numbers, what's it going to get close to? So in the formula, see how it has S equals A over 1 minus R? You might want to put a little subscript of 1 right there. That's the first term. So we need to know the first term, and then we're going to divide the first term by 1 minus R. So let's take a look at example 8. It says find the sum of the infinite geometric series. So we already know that this is the formula that we are using, and I already know that the first term is 2, but I need to find what R is. So I'm going to come back over here and do a little bit of work. I know the first term is 2. It's going to be multiplied by the common ratio, and it's going to give us the second term, which is 2/5. How do I get R by itself? Well, I would divide by 2. That's the same thing as multiplying by 1/2, which I'm going to choose to do that since I have fractions. And good news, those cancel, and I get a 1/5. So I now know that my common ratio is 1/5. All right, I like this one because we can do it without a calculator, can't we? Yes, we can. All right, so 1, I'm going to change it into 5/5. 5/5 minus 1/5 is 4/5. How do I divide fractions? That's easy peasy. I'm going to turn it into multiplying by the reciprocal. You can stick that 2 over 1. We can cross cancel because 2 goes into 4 twice. And so the sum of this infinite geometric series is 5 over 2. 2.5, 2.5, 5 over 2, however you want to write. Alrighty, y'all. Last one. Can you feel the excitement in the air? No, because you're not here, but it's here. Okay, so first term is a 3. Then I'm going to have 1 minus R. I don't know R. Let's do some work. So the first term times R gives us the second term, which is negative 3 over 2. I need to get R by itself. I could divide by 3, which is the same thing as multiplying by 1/3. Good news, the 3's cross cancel. I'm left with -1/2. Be careful right here. You need to make sure that you put that negative in there because you already have the minus sign from the formula, and now you need the negative sign as well. Well, what happens when you have those double negatives? We know that turns into a plus, right? I'm going to change the 1 to 2/2. I have 2/2. Remember, we're changing this to a plus 1/2, and that is 3/2. Again, we're going to change this to multiplying by the reciprocal, and the 3's cancel out, and the sum of the infinite geometric series is a whopping 2. Alrighty, that's it, y'all. I'm a little sad. I guess do the homework and let me know what help y'all need. Is this the last video? This might be y'all's last video. Oh, my heart. I'm so sad. Okay. Maybe I'll just make another video and talk to y'all later. Because, you know, I might get bored at the end of the week. Oh, my heart. Okay. I gotta stop talking to myself, talking to y'all, whatever I'm doing. I gotta stop. Bye, y'all.